So we're going to continue with our notes now on forces in motion. So far we have already covered what speed is, what acceleration is, and we've had an introduction to forces. So to get us back where we need to be, I'm going to start out with a review of what Newton's 3 laws were. So we're going to actually add on a couple of new terms in this section, but most of it should be reviewed because we had to talk a lot about Newton's 3 laws for your project. The new terms are going to be inertia and momentum. So I'll explain what those are. We're going to talk about inertia on our first slide, and then momentum will be the last thing that we'll cover in this section. So I know you guys can do this. No try. Do or do not. There is no try. Okay, I screwed that up. Let's move on. Okay, so the very, very top of this page, you're going to put the question, Newton established his 3 laws of motion to do what? And then Newton's first law of motion stated this way: an object in motion stays in motion, and an object at rest stays at rest until an unbalanced external force acts on it. Please make sure that you have both the term unbalanced and external when you're describing the force that's going to act on it. So remember, with your car projects, you had to have external sources of energy. I didn't want them to be internal, like the internal springs and so forth. So your balloons causing some external force on the object of the car. Internal forces are going on inside us all the time, but they don't actually cause us to move. So you've got your heart making motions, your blood is flowing through your body, but those are internal motions and forces and accelerations that don't actually cause your body to move around. We can also do internal forces to, flex and release our arms, and that's a little different than having an object that's being pushed along. And what we're trying to focus on are just the big idea, an object having external forces acting on it, and not so much all of the internal forces. That gets a lot more complicated. Now, this law, Newton's first law of motion, is very often described as the law of inertia. So we need to define what inertia means. Inertia is the tendency of an object to resist any change in its motion, and this is determined by its mass. The more mass something has, the more inertia it has. For example, if I've got this object here, this object is pretty heavy, and then my pen is pretty light. It's a lot easier for me to change the motion of this pen than it is for me to change the motion of my thing, whatever this is. I don't have a name for it. So heavier objects will resist a change in motion more easily, and that is both if they're at rest or if they're already in motion. Let's look at a couple examples. So here's some examples where objects were moving very, very quickly and then came to a sudden stop. So here's one. Your truck has brakes, the massive hunk of stone doesn't. So the idea is, as this truck is driving along, it's got a great big speed, and the hunk of stone inside also has a great big speed. And so when you slam on the brakes, because the brakes don't automatically touch the stone's going to slide forward, and in this case destroyed the cabin and hopefully didn't cause any injuries. This one, similar idea. You're biking along and trying to come to a sudden stop, but your body does not have brakes acting on it. The brakes are acting on these wheels here. So your body continues moving forward, and you do a lovely flip. And perhaps it's quite impressive if you can land on your feet. But I don't know that this guy will. Looks like he's going to lose. Okay. So those are a couple of examples. I wonder if you guys can think of any examples where an object would be at rest and their inertia keeps them from wanting to start moving. So see if you can think of a couple of examples like that. Now let's talk about Newton's second law. A net force acting on an object causes the object to accelerate in the direction of that force. So you guys had sources of energy or force to act on your cars. Some of them were balloons, some of them were rubber bands. So there was a force that caused your object to accelerate in the direction that the force was being applied. And the way we can remember this is, may the mass times acceleration be with you. Force equals mass times acceleration. Okay, so acceleration is determined by the size of the force and by the mass of the object. We can actually rewrite this equation, and the way that we could rewrite this equation, let me show you, would be to say that acceleration is equal to force divided by mass. So if I wanted to actually calculate an acceleration, I would do force divided by mass, and that's just rearranging this equation. So I'm solving for acceleration. To do that, to get this by itself, I have to divide both sides by m. On this side, it would cancel out, but over here you get force divided by mass. All right, so far what we should have is our question, the title of this section, Newton's first law, inertia, Newton's second law, F equals ma, and then this definition down here, its acceleration is determined by the size of the force and the mass of the object. And then I do want you to write out, may the acceleration, mass times acceleration be with you, as a reminder that force is mass times acceleration. Now we're going to write out this equation, and then I want to explain the unit for force. The unit for force is the Newton. And so we're going to look at this next slide here. So the unit of force, which is mass times acceleration, is the Newton. And what that actually means is kilograms times meters per second squared. So we're taking the unit for mass, which is kilograms. Mass is measured in kilograms. And then acceleration, which is in meters per second squared. We multiply those two together, and we get kilograms times meters per second squared. So this is like when you find a speed, you're taking distance divided by time. So the unit for speed is the unit for distance, meters, divided by the unit for time, seconds, meters, divided by seconds, meters per second. This is the same idea. We're taking the unit for acceleration times the unit for kilograms, because we literally, or the unit for mass, because we're literally multiplying mass times acceleration, so we multiply the units together. Now, scientists are lazy because they don't want to write a whole lot, and they like to write out these equations and formulas to make all of their writing a lot easier. So like this formula is a lot easier to write out than all of this crap. So instead of writing out this big giant unit, they decided to just use a capital letter N, and that would be it. So newtons is equal to kilograms times meters per second squared. So that's what the unit actually is for force. It's the unit for mass times acceleration, but we use capital N, newtons, for short. Last, Newton's law, Newton's third law of motion. This one is all forces come in equal and opposite pairs. And that means that they are happening at the same time. So that part really is important. I do want you in this section, all forces come in equal and opposite pairs. I want you to draw at least 3 examples from this slide here. So I'm going to come back here, pick 3 of these, and you're going to draw that in addition to writing down this definition, just like I showed you on that beginning slide. All right, the last term that we're going to talk about is momentum. Now, momentum is a property that frequently gets confused with force. Momentum is how much mass and velocity an object has itself. And its equation is actually very similar to the force equation. Momentum is mass in kilograms times velocity in meters per second. So the only difference is that we're using velocity instead of acceleration. So force is mass times acceleration, momentum is mass times velocity. And I don't have an easy way to help you memorize that one, unfortunately. The other thing that we need to make sure that we write down here is that the symbol for momentum is actually a lowercase p. I don't know why it's a lowercase p. M is already being used for meters and also for mass. So if you have another M for momentum, it could really make things complicated. So we've got P, momentum, is equal to mass times velocity. So we would write that P equals mv. Just like for force, we would write F equals ma. So very, very similar equations. But the other thing is there is no special unit for momentum. It's just kilograms times meters per second. I guess they decided since there's not the extra squared on it, we didn't need to mess with it. I think that maybe we should call them bovis. And that could be equal to kilograms times meters per second. But if you wrote that out, nobody would know what you were talking about, so you should probably not do that. Anyway, the point here is that momentum is how heavy something is times how fast it's going. So if something is stopped, that means it has no momentum. It has actually quite a bit of inertia maybe if it's very heavy. And so it's going to take a lot of energy to get it started. It's kind of like when you wake up in the morning and you're really tired and you don't want to get out of bed. And you're just lying there and you feel heavy. You don't have any momentum and you have a lot of inertia. You have a lot of resistance to start moving. Once you get up and kind of start going, you start building up momentum and it's easier for you to keep going. You still have inertia. Your inertia is actually the same because your mass is the same. It's just that now that you're moving, it's easier to keep moving and it's harder to stop. So the idea is that inertia is a resistance to the change, and then momentum is how much mass and velocity you have, both mass and velocity. Mass is the only thing that affects inertia. Both mass and velocity affect momentum. So in summary, we've got our three laws. The first law is also known as the law of inertia. If you're at rest, you want to stay at rest. If you're in motion, you want to stay in motion. So that's your inertia, your resistance to change. Second law, force equals mass times acceleration. A bigger force means a bigger acceleration. A bigger mass means you need a bigger force to accelerate. Third law, forces come in equal and opposite pairs. So if you've got one object pushing on the first object, the second object is pushing with an equal and opposite force back on the first one. Momentum is mass times velocity as opposed to force, which is mass times acceleration. Force is measured in newtons. Momentum is measured in kilograms times meters per second. Kilograms times meters per second. Unit for force, kilograms times meters per second squared, newtons for short. And that's everything for today. Thanks, guys.